In December 2024, the world witnessed a monumental achievement in the realm of quantum computing. Google's quantum chip, Willow, accomplished a computational feat previously deemed impossible. It solved a complex problem in a mere 5 minutes, a task that would have taken the world's most powerful supercomputers an unfathomable 10 septillion years. This breakthrough, documented in the esteemed journal, has sent shockwaves through the scientific community and beyond. Willow's success lies in its ingenious use of qubits, the fundamental building blocks of quantum computers. Unlike classical bits, which can only exist as a 0 or a 1, qubits can exist in multiple states simultaneously, a mind-boggling phenomenon known as superposition. This unique ability allows quantum computers to perform calculations at an exponentially faster rate than their classical counterparts. Adding to its prowess, Willow employs a novel error reduction method, a significant hurdle in the field of quantum computing. By incorporating more qubits into its architecture, Willow effectively mitigates errors, paving the way for more reliable and complex computations. This remarkable achievement has not only pushed the boundaries of quantum computing, but has also ignited a fiery debate about one of the most profound and perplexing ideas in modern physics, the multiverse. The implications of Willow's success extend far beyond the realm of theoretical physics. Its computational power holds immense promise for various fields, including medicine, materials, science, and artificial intelligence. As we stand on the cusp of a new era of quantum supremacy, the question arises: has Willow provided us with a glimpse into the enigmatic realm of parallel universes? Or is there a more grounded explanation for its remarkable capabilities? The multiverse theory, once relegated to the fringes of scientific inquiry, has found itself thrust into the spotlight, fueled by the recent breakthroughs in quantum computing. This captivating, albeit controversial theory proposes that our universe, vast and awe-inspiring as it is just one of many, perhaps an infinite number, of coexisting universes. Each universe, according to this theory, branches off from others as a result of quantum events, creating a cosmic tapestry of unimaginable complexity. The idea of multiple universes has long captivated the human imagination, appearing in ancient myths, philosophical treatises, and works of science fiction. However, it wasn't until the mid-20th century that the multiverse theory gained a foothold in mainstream scientific discourse. Hugh Everett III, a brilliant but unconventional physicist, first proposed the many-worlds interpretation of quantum mechanics in the 1950s. Everett's theory sought to address a fundamental paradox in quantum mechanics, the seemingly random collapse of the wave function. According to quantum theory, particles exist in a superposition of states until they are observed, at which point they collapse into a single state. Everett's radical proposition was that the wave function never truly collapses. Instead, every possible outcome of a quantum measurement is realized, each in a separate, parallel universe. While initially met with skepticism, Everett's many-worlds interpretation has gained traction among some physicists, particularly in recent years. The advent of quantum computers, with their ability to exploit the bizarre rules of quantum mechanics, has breathed new life into the multiverse debate. Could these powerful machines, capable of performing calculations across multiple states simultaneously, be tapping into the computational power of parallel universes? The recent success of Google's quantum chip, Willow, has reignited the debate surrounding the multiverse theory. Hartmut Neven, the visionary mind behind Google Quantum AI, has boldly suggested that Willow's extraordinary computational prowess might be explained by its ability to harness the power of parallel universes. This assertion, though speculative, has sent ripples of excitement and skepticism through the scientific community. At the heart of this debate lies the perplexing nature of quantum mechanics itself. Quantum systems, unlike their classical counterparts, can exist in a superposition of states, a concept that defies our everyday intuition. This inherent ambiguity, where particles seem to exist in multiple states at once, only to choose one when observed, has baffled physicists for over a century. Everett's many-worlds interpretation offers a radical yet elegant solution to this conundrum. By positing that every possible outcome of a quantum measurement is realized in a separate universe, Everett eliminated the need for a wave function collapse, a concept that troubled even the father of quantum mechanics, Niels Bohr. In essence, Everett suggested that reality itself branches off with each quantum event, creating a multitude of parallel universes, each with its own unique history and future. Could Willow's ability to perform calculations across multiple states simultaneously be a manifestation of this branching reality? Are we witnessing the first glimpses of a reality far stranger and more complex than we ever imagined? While these questions remain unanswered, the very fact that they are being seriously considered in light of recent scientific advancements speaks volumes about the profound implications of quantum computing. Proponents of the multiverse interpretation, emboldened by Willow's remarkable achievement, point to the very essence of quantum mechanics as evidence for their claims. The fact that qubits, the building blocks of quantum computers, can exist in a superposition of states, simultaneously embodying both 0 and 1, lends credence to the idea of parallel universes, each representing a different outcome of a quantum measurement. David Deutsch, a renowned British physicist and a staunch advocate for the multiverse, views quantum computers as prime evidence for the existence of parallel universes. He argues that the immense computational power of these machines, capable of outperforming even the most advanced classical computers in certain tasks, stems from their ability to tap into the vast computational resources of the multiverse. Furthermore, proponents highlight the elegance and self-consistency of the many worlds interpretation. By eliminating the need for a wave function collapse, an arbitrary and unexplained phenomenon in traditional quantum mechanics, Everett's theory offers a more parsimonious and intellectually satisfying explanation for the observed behavior of quantum systems. While the multiverse interpretation remains a subject of intense debate, the very fact that it can be invoked as a plausible explanation for the unprecedented capabilities of quantum computers speaks volumes about its growing influence within the scientific community. As we delve deeper into the quantum realm, we might find ourselves face to face with the astonishing reality of a universe teeming with parallel versions of ourselves, each living out different possibilities. While the multiverse theory has captured the imagination of many, it is not without its detractors. Critics, including prominent physicists like Ethan Siegel, argue that invoking the existence of parallel universes to explain quantum phenomena is unnecessary and ultimately untestable. They contend that alternative interpretations of quantum mechanics, such as the Copenhagen interpretation or the pilot wave theory, provide equally valid explanations for the observed behavior of quantum systems without resorting to the extravagant claim of multiple universes. One of the main criticisms leveled against the multiverse theory is its lack of empirical evidence. While the many worlds interpretation offers a compelling narrative, critics argue that it has yet to make any testable predictions that would distinguish it from other interpretations of quantum mechanics. The fact that Willow's achievement, while impressive, can be explained within the framework of existing quantum theories without invoking parallel universes further weakens the case for the multiverse. Moreover, skeptics point out that the problem solved by Willow, while computationally challenging, is a contrived benchmark problem specifically designed to showcase the power of quantum computing. It is not yet clear whether this computational prowess will translate into real-world applications that would provide tangible benefits over classical computing. Despite the lack of definitive proof, the debate surrounding the multiverse highlights the profound philosophical and scientific questions raised by quantum mechanics. As we continue to explore the bizarre and counterintuitive world of the quantum realm, we must remain open to all possibilities, however strange or unsettling they may seem. The search for a unified theory of reality continues, and the multiverse, despite its critics, remains a tantalizing possibility that cannot be easily dismissed. The concept of a multiverse, while seemingly fantastical, has deep roots in scientific thought. A century ago, the very notion of other galaxies beyond our own Milky Way was met with skepticism. Astronomers believed that the Milky Way constituted the entirety of the cosmos. However, Edwin Hubble's groundbreaking observations in the 1920s shattered this anthropocentric view, revealing a universe teeming with billions of galaxies, each an island universe in its own right. Could our current understanding of the universe be similarly limited? Just as the discovery of other galaxies expanded our cosmic horizons, could the discovery of other universes revolutionize our understanding of reality itself? Proponents of the multiverse argue that the seeds for multiple universes are sown within the very fabric of our cosmos. The theory of cosmic inflation, proposed in the 1980s, suggests that our universe underwent a period of exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion, driven by a mysterious force field, could have created bubble universes, each with its own set of physical laws and constants. Furthermore, cyclic universe theories, championed by physicists like Paul Steinhardt and Neil Turok, propose that our universe undergoes cycles of expansion and contraction, with each cycle giving birth to a new universe. These theories, while speculative, offer intriguing possibilities for the existence of multiple universes, each with its own unique history and properties. While the multiverse theory has captivated the imaginations of many, it is crucial to remember that it is not the only game in town. Several alternative theories offer compelling explanations for the enigmatic world of quantum mechanics without resorting to the existence of parallel universes. One such theory is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. The Copenhagen interpretation, widely considered the orthodox view of quantum mechanics, posits that the act of observation fundamentally influences the state of a quantum system. Before observation, a particle exists in a superposition of states, described by a wave function. However, upon observation, the wave function collapses, and the particle chooses a single definite state. Another intriguing alternative is the pilot wave theory, proposed by Louis de Broglie in the 1920s and later revived by David Bohm in the 1950s. This theory suggests that particles are guided by a wave-like field, often referred to as a pilot wave. This pilot wave determines the particle's trajectory, providing a deterministic underpinning to the seemingly random world of quantum mechanics. While the Copenhagen interpretation and the pilot wave theory offer different perspectives on the nature of reality, they share a common thread. They both attempt to explain quantum phenomena within the confines of a single universe. Ultimately, the choice between these competing interpretations, including the multiverse theory, rests on which explanation provides the most consistent, parsimonious, and experimentally verifiable account of the quantum world. Regardless of its implications for the multiverse debate, Willow's success represents a watershed moment in the evolution of quantum computing. Its ability to solve a problem deemed insurmountable for classical computers in a matter of minutes heralds a new era of computational power with the potential to revolutionize numerous fields. In medicine, quantum computers like Willow hold the promise of accelerating drug discovery by simulating complex molecular interactions with unprecedented accuracy. This could lead to the development of new drugs and therapies for currently incurable diseases. Materials science stands to benefit immensely from quantum simulations, enabling scientists to design new materials with tailored properties, from superconductors to ultra-efficient solar cells. Furthermore, the field of artificial intelligence could experience a paradigm shift with the advent of quantum machine learning algorithms. These algorithms, leveraging the principles of quantum mechanics, have the potential to analyze vast datasets and identify patterns far beyond the capabilities of classical algorithms, leading to breakthroughs in areas such as image recognition, natural language processing, and autonomous systems. Beyond these practical applications, Willow's success serves as a powerful reminder of the boundless potential of human ingenuity and our insatiable thirst for knowledge. The pursuit of understanding the universe and our place within it has been the driving force behind countless scientific breakthroughs throughout history. The ongoing debate surrounding the multiverse theory, fueled by the remarkable achievements in quantum computing, highlights the profound questions that lie at the heart of our quest to understand the universe. Are we living in a single solitary universe, or are we merely inhabitants of one branch on an unimaginably vast cosmic tree teeming with parallel realities? While the answer to this question remains elusive, the pursuit of knowledge itself is its own reward. The scientific method, with its emphasis on observation, experimentation, and rigorous analysis, has proven time and again to be our most reliable guide in unraveling the mysteries of the cosmos. Whether or not the multiverse theory is ultimately proven, the very act of questioning our place in the grand scheme of things, of daring to imagine possibilities that stretch the limits of our current understanding, is a testament to the indomitable spirit of human curiosity. The journey of scientific exploration is as important as the destination, and each new discovery, each tantalizing clue, brings us one step closer to unveiling the true nature of reality. As we stand on the precipice of a new era of scientific discovery, with quantum computers like Willow illuminating the path forward, we must embrace the unknown with a sense of wonder and a commitment to pursuing truth wherever it may lead. The universe, with all its beauty, complexity, and enduring mystery, awaits.